So this text section, I'm going to talk about Mark-Houwink equation, which shows relationship between intrinsic viscosity with the molecular weight, and is a power law relationship, and that's what it looks like. And later that for polydisperse sample, this was just shown up as a viscosity average molecular weight. So for the polydisperse sample. So the way that it works is, this is an example of polymer with different molecular weight, and they measure the intrinsic viscosity. And then once again, intrinsic viscosity has a unit of inverse concentration, that is volume divided by mass. And when you plot this on a log scale, log intrinsic viscosity, people find out it follows some linear relationship. Okay, to remember my first homework assignment to you, you have changed the number of random walks, n, versus the end-to-end distance, which is an h, and then I plot it as a log-log plot. In the log-log plot, the linear line means that's a slope. And this slope, and he called it A. A has a meaning here, which is a Mark-Houwink constant A is shown up here. And A value can ranges from 0.5 to 0.8. And that was somebody's work. So this is you can think about, that's a practice that people has done it before. So somebody actually has make the polymer that is well-defined molecular weight, just like this, and measure the intrinsic viscosity. So making this sample, and you do the molecular weight measurement by, let's say, light scatterings or osmotic pressure measurement, so you know the values. And then you using the capillary viscometer to measure those. And then these two are correlated. Now you have found this value. And this is essentially somebody's very a lot of work for somebody doing this. And here's an example of actually the list of the polymer samples and their K and A value. If you look at the A values, it ranges, with the exception of sometimes it's out of the bound, but typically it ranges from 0.5 to 0.8. Okay, that's the ranges that you have. And then if you actually have a 0.5, this is closer to the theta solvent. And if you go to the A, that's close to the good solvent. I'm going to talk about this one later. But this Mark-Houwink equation coming from strictly from very empirical understanding. The higher the polymer molecular weight it is, right? The higher the intrinsic viscosities are, right? If you increase the molecular weight here, you will see the increase in the intrinsic viscosity. They're trying to find the correlation in the power law format, and that one works out very much. And this is a tabulate in the polymer handbook, and there's a lot of polymers has to be was listed there. And you must list what kind of solvent and what's the temperature for given polymers that is shown up here. So polystyrene, for example, there's an example of toluene versus cyclohexane. The cyclohexane is one that has showing up the A constant to be 0.5, whereas a good solvent is somewhat bigger. Okay, and there are other polymers that they're doing the same. When he write a theta means That's a theta solvent, and then that's a power law is close to zero. That's just an additional addition. And this is a Mark-Houwink parameters, and then it's very powerful for the one that people use and to correlate that. And essentially, the higher the molecular weight it is, the higher the intrinsic viscosity. And that correlation was founded here. Later, people has a meaning of this power law A in the significance, and also the meaning of the K, which is to a lesser extent, but they have find a way to correlate those to something more fundamental, what we call the solvent qualities for the Cherenkov extension.